Hello everyone. So welcome to IIT Engage classes. It's the continuation of our discussion for gas dynamics topics. So today's topic is flow with friction and heat addition. So what we are going to see in today's session is, so we take a constant area duct and what happens if I add the heat, or what happens if I consider the effect of friction and the flow is moving in a constant area duct. So that's the part we are going to address today. So like till this session, so we treated our flow condition with an adiabatic assumption where there is no heat transfer, and inviscid scenario with there is no friction. So today we are bringing in that complexity. It's more close to a realistic scenario. But still we are reducing our problem greatly, because whenever I am adding heat, I am not considering the effect of friction, or whenever I am considering the effect of friction, so I am not adding the heat. So that's the two part like we are compromising with. But we are just studying like what happens if I only add the heat into the constant area duct flow, or what happens if I consider only the friction effect in a constant area duct flow. So that's the part we are going to address. So it brings you the glimpses of how practical problems looks like, how complex simple flow physics can become the moment when I consider the key variables such as heat transfer or the friction, right? So myself Akshay. So let us move on to the topic. So first we will deal with the flow with the heat addition. So simple schematic of the problem, the control volume problem, you can say I have a control surface 1 where I have a flow properties, say like Mach number 1 or density rho 1, temperature T1 or pressure P1, like that, right? So at the station 2 I have Mach number M2, rho 2 density, temperature T2, pressure P2. Similarly, I can also define stagnation properties like T01, T01. So here also T02, T02. A very simple problem. And so there is a flow which is coming at this upstream properties and flowing through a duct and exiting from the duct at area 2. Area 1 is equal to area 2 as it is a constant area duct. And what I am doing is, so I am just adding some heat, or I am taking away some heat. So I am allowing the heat transfer to occur. I am not giving any constraint on the way which the heat is transferring, whether it is isothermal heat transfer or any other process. So that's not I am defining as of now. I'm just saying like if I add the heat or remove the heat, that's it from the system. Okay. So basic governing equations are simple. So as it is 1D flow, one dimensional flow, so flow is having in this direction, and I'm treating uniform properties in any given section. So with all these assumptions, so we have done it numerous times by now. So we all know how the governing equation looks like. The continuity will be like rho 1 u1 is equal to rho 2 u2, and my momentum equation is p1 plus rho 1 u1 square is equal to p2 plus rho 2 u2 square. Similarly, the energy equation, here we see the difference because now I have a heat addition. So H1 plus U1 square by 2 plus addition of heat is equal to change in enthalpy H2 plus U2 square by 2. Simple, right? So for simplicity, I am writing all the governing equation we are going to use for the problem. Continuity, momentum, energy, enthalpy is a variable which relates enthalpy to the temperature. So if I do so, you should be able to recognize the form, because if I use in this form, that means I am treating it is calorically perfect gas. It's again simplified version of the bigger problem. And of course, equation of state, which is valid for any given point in flow field, right? So these are the equations I am going to use, and we can reduce the equations to a required form. The first thing we are going to see now is the energy equation. First, we will see what happens to energy equation. So what I have is, so I am writing, I am using the help of enthalpy relation, CpT1 plus U1 square by 2 plus Q is equal to CpT2 plus U2 square by 2. So I can write for the heat alone, Q is equal to Cp times T2 minus T1 plus 1 by 2 times U2 square minus U1 square. Or I can write in another form, what is this CPT plus U1 square by 2? Locally, this is nothing but a stagnation condition, right? With the assumptions, whatever we consider for the definition of stagnation temperature. So for calorically perfect gas, so this is nothing but a stagnation temperature. So Q is nothing but Cp times Cp times T02 minus T01. So this is what change in the total temperature. It's a change in total enthalpy, nothing but the addition of heat is nothing but the change in total enthalpy. This scenario we might encounter while solving the uh, problems such as uh, in propulsion. If you can recall your basics, so you might have solved these kind of problems in uh, combustion analysis, right? Like where you want to calculate the fuel to air ratio and all. So there you use this similar form of energy equation where heat transfer is involved, right? So now the change in total enthalpy is nothing but the either addition of heat or removal of heat, that is governed by whether this T02 minus T01 is positive or negative. If it is positive, that means you are adding heat. If it is negative, that means you are removing the heat, right? So it's a straightforward, the energy equation. So by this point, you can recognize there is a change in total temperature. Unlike in our other cases, for adiabatic flow process, we treated T0 is constant. But in this case, it's not constant because there is a change in heat, right? Okay. So now, we did it for normal shock waves and other things. What we did is like to change, see the property change, right? P2 by P1 or T2 by T1 or rho 2 by rho 1 or even total properties P0 2 by P0 1 or T0 2 by T0 1, like that. So this is the same thing we are going to see now with the heat addition, right? Like from the area 1 to area 2, what is the property changes, how the properties are changed. So that's what we are going to see. So for that, like I am going to alter my governing equation a little bit. So we have rho u square form. So what I'm going to do is I'm using the definition of Mach number. Mach number is nothing but the local speed to the local speed of sound. So u by a. So u I can write in terms of Mach number times the local speed of sound. So rho into u square. So that is m square a square. And the definition of a is nothing but square root of gamma p by rho, or a square is gamma p by rho. So I can also replace this with rho into m square times gamma p divided by rho. So rho and rho can get cancelled. So this becomes gamma p times m square. So why I am using this one is because in momentum equation I find this kind of term rho into u square, right? So now coming back to our momentum equation. So P1 plus rho 1 u1 square can be written as gamma P1 times M1 square is equal to P2 plus again rho 2. Sorry, this rho is cancelled. So rho is not there. So we are writing rho into U square in terms of gamma P M square. All right. So gamma P2 M2 square. So now what I am doing is I am taking P2 minus P1 form. P2 minus P1 is nothing but if I take gamma P2 minus P1, right? So gamma P1 M1 square minus gamma P2 M2 square. So now if I take P1 common from both equations, so what both sides, so it happens P1 times P2 by P1 minus 1, which is also equal to gamma P1 times M1 square minus P2 by P1 times M2 square. So from both sides P1 can get cancelled. So now I can write it for the P2 by P1 because here also I have P2 by P1, here also I have P2 by P1. So if I do so, so what happens is P2 by P1 plus gamma P2 by P1 times M2 square is equal to gamma M1 square plus 1, right? So now if I take P2 by P1 common, what I get is P2 by P1 1 plus gamma M2 square is equal to 1 plus gamma M1 square. So I got P2 by P1 as a function of Mach number. So that is nothing but 1 plus gamma M1 square divided by 1 plus gamma M2 square. So this is my P2 by P1 relation. So similarly, what I can do is I can also write it for T2 by T1. T2 by T1, what I am going to do is like I am going to take the help of equation of state. So I can write T2 by T1 as P2 by P1 times rho 1 by rho 2. How I am doing this? I am writing P is equal to rho RT relation. So T can be written by P by rho 2 R and T1 can be written as P1 by rho R. So R get cancelled, so I get in this form. So what is rho 1 by rho 2? Rho 1 by rho 2, I can use the continuity equation. Rho 1 U1 is equal to rho 2 U2. So rho 1 by rho 2 is nothing but U2 by U1. So I can write in terms of P2 by P1 times U2 by U1. Now what we can do? So this U I can represent in terms of Mach number. So that is nothing but M into A. So that becomes P2 by P1 into M2 A2 divided by M1 A1. Right. So again A2 by A1 I can use the definition of sound, that is root of gamma RT. So gamma R get cancelled. So this becomes P2 by P1 times M2 by M1 times root of T2 by T1. So in the left hand side I have T2 by T1, right hand side I have root of T2 by T1. So this becomes root of T2 by T1 is equal to P2 by P1 times M2 by M1, right? So now just square on both sides. So what you get is T2 by T1 is equal to P2 by P1 whole square. So we already solved for it. So 1 plus gamma M1 square divided by 1 plus gamma M2 square, the whole square, squaring both the sides, M2 by M1 whole square. So this is a T2 by T1. And if I want to calculate rho 2 by rho 1, again the same process, rho 2 by rho 1 can be written as P is equal to rho RT. So I can easily write in terms of P2 by P1 times T1 by T2. So use the definition of P2 by P1 and T2 by T1. So that should give you 1 plus gamma M1 square divided by 1 plus gamma M2 square times this is inverse of T2 by T1. So if I use that one, I get 1 divided by 1 plus gamma M1 square divided by 1 plus gamma M2 square multiplying M1 by M2, sorry, inverse, right? M1 by M2 square. So I can the whole square this one. So 1 and 1 term get cancelled. So it gives you 1 plus gamma M2 square divided by 1 plus gamma M1 square times M1 by M2 whole square. Straightforward. So we got P2 by P1, T2 by T1, rho 2 by rho 1. How can we calculate P0 2 by P0 1 or P0 2 by P0 1? That is again straightforward. I am not going to show you the derivation part and all. So I am just going to show you how you can do it. So P0 2 by P0 1, what you can do is you can divide and multiply P0, P2 and P1. So P0 2 by P2 into P2 by P1 into P1 divided by P0 1. So P0 2 by P2 is nothing but a point definition, right? At the point you are applying. So you can use the isentropic relation, that is nothing but 1 plus gamma minus 1 by 2 times M square to the power of gamma by gamma minus 1. So that you can use. So that is 1 plus gamma minus 1 by 2 times M2 square to the power of gamma by gamma minus 1 times P2 by P1, use this relation, and again P1 by P0 1, same way, 1 by 1 plus gamma minus 1. So in this way you can represent in terms of Mach number. Similarly for T0 2 by T0 1, the same process. What you can do is you can write T0 2 by T2 multiplied with T2 by T1 multiplied with T1 by T0 1. So again use T0 2 by T2 as isentropic relation or M2 square to the power of if this is not required because T0 by T2 is this one. T2 by T1, use this definition times again 1 divided by 1 plus gamma minus 1 by 2 times M1 square. So in this way you can actually write the T0 2 by T0 1 relation. These relations are fine. So how we can obtain and those things. What is important here is like what we have seen so far is all these properties like T2 by T1 or P2 by P1 or rho 2 by rho 1 or even stagnation properties P0 2 by P0 1 or T0 2 by T0 1. All of them I am representing in terms of function of Mach numbers, not just the Mach number. Whatever we got so far, you see, I have both M1 and M2 in the expression. So this is important here because what we saw for normal shock wave and other things is that like we had a function of upstream property alone, upstream Mach number alone. But in this case, it is not the same. So this is a bit tricky here because we have to know both the Mach numbers to get the property change. It becomes a bit difficult, right? If I given the upstream properties and the heat transfer, can you calculate the downstream properties at some point? So that's the question. So because both M1 and M2 are changing and it depends on the heat added, and it becomes a bit difficult for us to solve. So for that, what we actually do is we fix one of the Mach number to a reference value. Say what happens if Mach number reaches unity. So M1 becomes 1 at some point, right? So it becomes 1. So how much amount of heat you have to add to make it to become M is equal to 1. So that is the thought process you are going to do, and you write in terms of so T by T star. So note here, this T star is not characteristic temperature definition. This is the temperature for which a Mach number becomes 1 by removing or adding the heat in the constant area duct. So it's different because characteristic temperature is defined based on an adiabatic assumption. But clearly this is not an adiabatic flow because there is a heat transfer inward. This is just the temperature for which the flow becomes sonic, or when I add or remove the heat in the flow. We still don't know whether adding the heat or removing the heat make it possible. Unless and until I know the upstream condition, I can't state about whether this T star is so to reach the Mach 1, whether I have to add or remove the heat. So I don't know. It depends on the upstream Mach number, like whether it is supersonic or subsonic. So based on that changes. But the idea here is we are fixing it as a reference. The unique thing about this unique thing about this Mach number reaching unity is whatever may be your upstream condition, there is one unique point at which your Mach number reaches unity for a given gas properties. Calorically perfect gas, you are going to reach one particular unique point. So usually we use Molnier diagram like HS diagram or TS diagram to analyze it. So let us see this problem, the bigger problem, in a more pictorial way. Say I have a Mach number 1, so M1, a supersonic, M1 is equal to 3, and I have M2 is equal to 1.5, right? So what I'm doing, I'm adding heat so that the Mach number at this point is reaching Mach number at 1.5. So amount of heat I am adding over here, let us say it as Q1. Okay, so now you see, same station 1, I have M1 is equal to 3. Now I am adding Q1 star represents a heat added to reach the supersonic flow into M1 condition. M is equal to 1. So for that I am adding Q1 star heat. So now let us take a station 2 where a Mach number is 1.5. Now again I am adding some amount of heat, say Q2 star, to reach unity. So now you see the beauty of this. So the values which attained at M is equal to 1, the P star, rho star, T star, or P0 1 star, T0 1 star, they are same whether I am approaching from M1 is equal to 3 or whether I am approaching from M2 is equal to 1.5. It doesn't matter from which Mach number I am approaching to this value, but these values are going to be same. So that means Q1 star is nothing but Q1 plus Q2 star, or I can write in other way, Q2 star is nothing but Q1 star minus Q1. So Q1 star is the amount of heat required to make this flow from Mach number 3 to Mach number 1, which is also equal to amount of heat needed to make this flow from M1 is equal to 3 to M2 is equal to 1.5 plus M2 is equal to 1.5 to M is equal to 1. It's the same thing because these properties are same at M is equal to 1 for the given pressure, temperature, or density, or for a given calorically perfect gas at this given condition. Right? This one I am not changing. This is important. This point I am not changing. P1, T1, rho 1 point. Right? So similarly, P2, T2, rho 2 at station 2 are not going to change as long as I am using the same gas. Right? This is interesting. So based on this, we can actually have a TS diagram like this. This is TS diagram, Molnier diagram. So this one is called Rayleigh curve when I have a heating or cooling effect. So in a constant area duct, this type of curve is called Rayleigh curve. So here you see what's happening. So when I have a supersonic flow, say M is greater than 1 at point 1, some Mach number is there, it's supersonic. So now if I add the heat, what happens is the flow as the flow happens and when I add the heat to the flow, so the supersonic flow will decelerate and reach towards sonic condition at point A. This is the point where I have a maximum entropy condition. Beyond this, if I add any heat, it's not going to affect the curve. So because after this, my curve stops. So similarly, if I have a subsonic flow and if I add the heat, again, the flow will reach towards sonic condition. So here you can see one more point. This is the point of maximum temperature. The point of maximum temperature and maximum entropy are not the same, right? So this point corresponding to 1 divided by root of gamma for a given calorimetric property, this point. So till this point, the adding the heat into a subsonic flow will result in increase in temperature. After this point, there is a short duration till it reaches sonic condition. There the drop in temperature occurs. The involved part we are not going to discuss, is out of scope for us, but this is this point is important to know. Adding heat in subsonic flow is not always going to increase the temperature of the fluid. So it's up to certain point it increases, then it starts to decrease till it reaches sonic. But whereas in supersonic flow, it is not the condition. Adding heat will increase the temperature of the fluid. Okay. So in both the cases, what is happening? Adding the heat will make the flow to reach towards sonic flow. That is important. And cooling has the other effect. If I add the, if I remove the heat from the supersonic flow, the flow will accelerate. Whereas if I remove the heat from the subsonic flow, it will decelerate. So this is important. Okay. So this curve is very, very important for a gate point of view. So based on this, you might get questions in your gate. So the point A is actually called a thermal choking point. Thermal choking. So we already discussed what is choking is all about during the convergent divergent nozzle flows. The choking there we defined it's the condition where the mass flow rate becomes independent of any changes in the downstream property. So it becomes constant for a given upstream flow. So here also for a given upstream flow, adding further heat is not going to change the properties at m is equal to 1. So it reaches m is equal to 1 at some point and then it is not going to change anything. So what it actually does in physical practical scenarios is, so it is going to alter the upstream condition to adjust to the new values. So that's what it does in a broader picture. But so this point is called choking because further addition of heat is not possible to this particular flow at given duct at a given constant area with a given upstream condition. So you can't add more heat, right? So it's a saturation point. So that is why it's called thermal choking. Okay. So this is all with the flow with heat addition. And similarly, we have like these things we can list down what happens if I add the heat in the supersonic region and what happens if I add the heat in subsonic region. So it is so you guys can go through it. Whatever we discussed so far, that's what's going to happen. So let us see other properties also. We discussed with respect to Mach number alone. Let us see what happens to pressure. The pressure will increase as I add the heat in the supersonic region, and temperature also increases as I add the heat. This we already saw in the diagram. The total temperature increases. This is yeah, well-known fact that because Q is equal to Cp times T02 minus T01. If Q is positive means if I adding heat, that means total temperature is increasing. Just straightforward. Total pressure decreases. This is the case because entropy is increasing. You have to see. Somehow you have to make sure the increase in entropy is resulting in some kind of a loss. That is nothing but the total pressure loss. This is always going to decrease irrespective of what kind of flow you are treating. This total pressure always going to decrease. Okay, the velocity decreases because Mach number is decreasing, right? Now, in a subsonic region, this is interesting part. When heat is added, all these things are written for when heat is added. This all flips when you when the heat is going to remove. Okay, so that's a straightforward guess you can actually make. No problem. So in a subsonic flow, if I add the heat, Mach number increases, pressure decreases because here increasing, here it is decreasing, and temperature is one property which has different behavior. Up to m is equal to 1 by root of gamma, it is going to increase, and after that it is going to decrease. That's we already saw. So that's the point of maximum temperature in the graph. And the total temperature increases, obviously, because you are adding the heat, again the same relation. So this one you see, this total temperature in both cases is going to increase if I add the heat, because it's a straightforward calculation you can actually make by using the energy equation, right? So now the total pressure is actually going to decrease. This is also same for whether it is supersonic or subsonic flow, because entropy is increasing in both cases when I add the heat. Velocity increases because accelerates. Fine. So now we will go to flow with the friction. Now, what I did in the last part is I added heat without considering the frictional effect. Now what I am going to do is, like, I am considering the friction effect, but I am not considering the heat transfer effect. So I still treat this flow to be adiabatic now. There is no heat transfer involved in this analysis. Okay, so I am just seeing the effect of friction alone on the flow. Okay, for this the control volume is same, but say like I have a station 1 and station 2, all the properties M1, T1, Rho1 like that, and this is my direction in which the flow is happening, and the length of the duct is given by L, and let us take a small segment of the duct with the small excursion dx over the length L. So within this one, whatever happens, that we are going to see, and we are going to integrate for the entire control volume. Whenever I have friction, that means a friction is opposing the flow, right? It's a resistance to the flow. So that is usually quantified using the shear stress or the wall shear stress, tau W. That is my shear stress. Okay. So now let us say the duct diameter is d, so that's constant. Okay. So now I have my governing equation for the 1D flow with the friction in an integral form, that is a control surface integral of a convective derivative. So still I am treating it as a steady flow. I'm not taking into an account of unsteadiness. Okay. So is equal to minus PDS in x direction. So I am just because my flow is happening in x direction, so I am only treating the 1D flow and x direction momentum equation. Remember, this is nothing but a momentum equation, okay, in an integral form, where we have the effect of friction, right? So where ds is nothing but the small volume, I can write in terms of pi d, small surface area, pi d L if it is a whole area. So, or I can write circumference of the duct times the small length dx times pi d is my circumference. So that is what my ds is. Let me write properly. Pi d times small expression dx. That is my small area. Okay, so this part I can write in terms of rho 1. The same thing we done earlier, so I am not going to give you the details. A is constant, so I am just treating it as A plus rho 2 u2 square A is equal to TDS x. So P1A minus P2A minus, this is 0 to L pi d tau w, so here times P. So now my integral equation becomes a bit simpler, and all I can do is write in terms of P2 minus P1. I'm just shifting everything to left hand side times A. So I'm just taking A constant from all the terms plus rho 2 u2 square minus rho 1 u1 square times A. So I'm shifting that to other side minus 1 divided by A times the integral 0 to L over the length pi d tau w dx. So what is area? Area is nothing but pi d square by 4. So I can write in terms of 4 divided by pi times d square integration 0 to L pi d tau w dx. Since d and pi are constant, so for a given duct, so pi get cancelled, d and 1d get cancelled. All I get is minus 4 divided by d times over the length tau w dx. So this is from an integral perspective. If I write the same momentum equation for a differential volume, that the small of a small expression dx, so I can write for a differential form of this equation like dp plus. So just see the last equation. I'm just writing the same thing. This is nothing but dp, small change in the pressure, plus this is nothing but d of rho u square, this one and this one. That's what I'm writing, right? So I'm just getting rid of that integral is equal to minus 4 tau w divided by d times dx. Okay, over the small length dx. That's what we are integrating. So that becomes like a differential form of this equation, where I can write this one as d of rho u square, right? So what I can do, I can write this one like rho, I'm taking rho u times pu plus u times d of rho u, right? So what is this one? Rho into u is equal to constant, that is continuity equation. So this term can be cancelled out because d of rho u becomes 0. Rho u is constant. So from the continuity, so this gives me just rho u tu. So I can write this second term in this way using the with the help of continuity. So that is dp plus rho u du is equal to minus 4 tau w divided by d times dx. Fine. So now we got into some differential equation. Now this calculation of tau w as a function of x is not that easy job. Okay, so all we can use is the empirical ideas, because tau w is proportional to the velocity squared. That's the drag. You have used it in your aerodynamics and all, right? So the drag can be written as half rho u square times cd. So here I am using the frictional coefficient f. So that can be modeled. So this is a model, okay? It's not a, physical explanation. So it's an empirical idea. So we are just treating tau W is proportional to a frictional coefficient F in this way with the multiplication factor, that's half rho u square. So it's related in this, where F is an empirical constant. So what you do is like you do a series of experiments and you try to fit the curve and you try to find that F. So what you usually do is like you calculate the drag and you calculate the half rho u square and you plot it as a linear graph and get the slope, and that should give you the value of F. So that's the traditional way to do the empirical relation. So they have a relation in this way. Okay. So now why is important? So now I am replacing this tau W in this form. So I can write dP plus rho u du is equal to minus 4 by d times half rho u square times F times dx. So now 2 ones are 2 2s are. So this goes like minus 2 rho u square divided by d times, or I can write in the other way only, half rho u square by d times 4 F. Let me take this d inside. Whatever, so it doesn't matter where you are taking. Just the form usually given in the text. Okay. So now what you see is, now you see some kind of a differential equation. Now you can integrate from point 1 to point 2 to get the effect of friction. Okay. So this is not a trivial. Okay. So this is going to be bit involved derivation. I'm not going into the details of the derivation. I'm just leaving at this point. What we got now is, we got for relation. So say like 4F dx divided by d is equal to, I'm just shifting that minus to other side, or let me write minus 1 by 2 rho u square 4f dx by d is equal to dp plus rho u du. So this is the relation we got. So now all we can do is integrate from all the way from 0 to L, and all these variables can be represented as a function of Mach number. So ultimately what you get is, so here you get 4f dx by d, which is integrated over 0 to L, which is also equal to some integration from m1 to m2 from this one as some function of Mach number times dm. So this is what you are going to get at the end. If you for that, like what you are going to do is like you are going to get the help of all these relations we obtained so far. A square can be written as gamma p by rho, or m can be written in terms of u by a, or even rho into u is constant, and all these things you are going to represent in terms of Mach number, and you get the form with the Mach number, right? So this is where I am going to stop the derivation, because the further derivation is not that important for the discussion. So all we have to understand here is like we can represent this as a function of Mach number. Okay. And this is going to give you the idea of how the friction is affecting the flow. This length, if I increase the length, the friction is also going to increase, because as the length increases, the friction also increases, because we are integrating over the length. Okay. So now, and other properties, they are simple. So the change in T2 by T1, so that you can always get using energy equation P2 by P1, rho 2 by rho 1. They are all the similar procedure what we have done for the flow with heat addition, the same way you can do it, but only the effect of friction that is actually given in an integral form as a function of Mach number, where you have to solve for the integral. And again, I'm stressing out this F is not trivial because it's an empirical relation. So it depends on whether the flow is laminar or turbulent. It's depending on that, like that, that empirical value of F can change. So that is very important. So it's actually a function of the length. It's a function of the x direction. The F is function of x, and you can integrate with respect to x. Okay. So all these things can be written as again a function of m1 and m2. So this is the same thing. So now again the question comes how to solve it. For that, again, what we are going to do, we take a reference as a flow when it reaches the sonic condition. Say I have a duct with some m1 which is equal to 3, which is going to reach m2 equal to 1. So for this, how much of length of the duct I have to need for a given frictional coefficient, that is f of x. Okay, so if the frictional coefficient of this duct is f of x, and if for some length of this duct L, I am going to get a supersonic flow at m1 is equal to 3 to m2 is equal to 1, right? So this one I am going to call it as L star. That's the length of the duct needed to make sure the friction is bringing the flow from supersonic to sonic condition. So this L star can be varied depending on the empirical relation f of x, whether the flow is laminar or turbulent. This is a much more involved problem. Let us take one condition: the flow is fully developed and laminar. For that, some f of x we will get. For that, we can calculate L star. Similarly, if I have m1 is equal to 1.5, say somewhere over here it is reaching 1.5. So now from here to here, again I am going to get some length L2 star, for which m2 is equal to 1.5 is going to reach m is equal to 1 condition. So this is L2 star. So for the same f of x, so same frictional coefficient value, right? So this is my reference now. So since this can reach m is equal to 1 condition, this part is this point is going to be called as choking point. Again, this is choking in the sense further increase in the length of the duct is not going to help you in reducing the Mach number. So that's the saturation point for that. So how can we analyze it? Again, using the curve such as Fanno curve. What we do here is, what we can see here, this is the increase in length. If I have a supersonic flow, m is equal to greater than 1 at some station 1, if I increase the length of the duct, the flow is going to decelerate because of the action of friction, the effect of friction. And it reaches a maximum entropy point where m is equal to 1. It is called choking point, right? Similarly, if I increase the duct length in a subsonic flow, what it actually does is, it increases the flow Mach number, or it accelerates the flow, and it reaches 1. In this case, there is no increase and decrease effect. It's always going to increase the Mach number, and temperature is always going to decrease if I increase the length. Whereas in the supersonic case, the temperature is always going to increase with increase in length, right? So you can see. So it's a straightforward scenario. You can easily analyze with the graph, right? So now you can see the physical picture of this problem in this way. Say I have a constant area duct, right? So what happens? The effect of friction brings the formation of boundary layer that increases as the length increases. Okay. So now you see, if I have a subsonic flow, what it effectively sees is the effective area is converging. So we know from our basic understanding, the subsonic flow, when it sees the converging area, it accelerates. Similarly, when the supersonic flow sees the converging area, it is decelerates. So that is another analogy through which you can understand this problem. I'm proud of it. So after a certain point, it reaches the fully developed condition where the boundary layer thickness becomes constant. So it is no more going to increase. Okay, it is not like a flat plate boundary layer kind of scenario. It's a boundary layer within the channel. So it reaches a fully developed state and it becomes a constant. So after that, the throat, it acts as a throat and as a constant area duct afterwards with this throat effective area. So there m is equal to 1 is reached and it is always going to be same. So this is just an analogy, okay? It's not the same way it should work. But this development of boundary layer, that is always present. So you can understand in this way, okay, as an analogy. More importantly, you have to remember here is like in a subsonic flow, the increase in length of the duct is going to decrease the Mach number and it reaches the sonic condition. And again, in supersonic flow, the increase in duct length will decrease the Mach number or decelerate the flow and reaches the sonic condition. So after sonic condition, the further increase in duct is not going to help. It stays at Mach number is equal to 1. In reality, what happens? It is going to change the upstream condition. So and readjust the flow peak. So that's what happens in reality. But for a given upstream condition, there is a choke. After that, there is no effect of increase in length. Okay. So this is all about flow with friction. So similarly, you can do the other property change across the duct, like with the friction. Similarly, what we have seen in the effect of heat addition. Here also you can make those things out. So see, like Mach number decreases with the increase in friction or increase in the duct length. That means the increase in overall friction. Not the friction coefficient, it's the tau W, that's the shear stress, it's going to increase. Okay. So now the pressure increases for a supersonic flow and temperature increases for a supersonic flow. That we have seen in the TS diagram also. Total pressure, as always, is going to decrease because there is a frictional loss that's going to contribute towards increase in entropy or decrease in total pressure. And velocity decreases because flow is decelerated. In subsonic case, again, Mach number increases, pressure decreases, it's opposite to what happens in supersonic case. Temperature decreases here, it's not going to increase like in heat addition case. So this Fanno curve is kind of a converging curve. So whereas Rayleigh curve, what you see, both of them, the subsonic branch and the supersonic branch, they tend to increase in temperature, right? But in this case, the temperature decreases for subsonic case. Total pressure decreases because of the friction effect. Velocity increases because flow is accelerated, right? So these tables are important for heat addition or for friction, for gate point of view. So don't make a mistake in these things. You can remember this. If you look at the graph, you should be able to understand this, especially pressure and temperature. You should be very careful. Okay, that's where you can make a mistake. Okay, so that concludes our discussion on flow with friction as well as with the flow of heat addition. So now let us take a few questions from gate. Okay, which of the following options can result in an increase in the Mach number of a supersonic flow in a duct? So they are giving option A as increase in the length of the duct. So this is not correct, right? Just now we saw like increasing the length of the duct in a supersonic flow is actually decelerate the flow. So you cannot increase the Mach number. So this is not correct. Adding heat to the flow. If I add the heat to the supersonic flow, so again from the Rayleigh curve we saw that. So adding heat is not going to increase the Mach number. It's actually going to decelerate the flow. So it decreases the Mach number. So this is also not correct. Removing the heat from the flow, it's correct because if I cool the duct in a supersonic flow, we saw that like the cooling has an effect that it increases the Mach number in a supersonic flow, whereas in subsonic it decreases. So it's reverse. Okay. So in a supersonic flow, if I want to increase the Mach number, so I can remove the heat from the constant area duct. So the last option, inserting convergent divergent section with the same cross-sectional area at its inlet and exit. Just to confuse you, We know if it is a supersonic flow, adding converging diverging nozzle is not going to increase the Mach number, it is going to decrease, because the moment the supersonic flow sees the converging section, it is going to decelerate the flow. It's a classic case of supersonic diffuser. So it's not correct. Okay, so it's a straightforward question. Okay, so now there is one interesting question is asked into 2017 gate. Consider a steady one-dimensional flow of a perfect gas with a heat transfer in a duct. Okay, so this the diagram, whatever they are given, TS, it's for the heat transfer. Okay, it's a flow with heat transfer. Okay, the TS diagram shown both the static and stagnation condition at the two locations A and B in the duct. AT and BT denotes the stagnation conditions for the states A and B respectively. It is known that delta TA is equal to delta TB. MA and MB are the Mach numbers of the flow at locations A and B. Which of the following statement is true about the flow? So they are given the scenario and the graph is given to you. So where point A and point B are 2 points in the constant area duct with the heat addition. So AT and BT represents a local stagnation condition for point A and point B respectively. So what they are given, the delta TA is also equal to delta TB. So what is delta TA? So this is nothing but T naught A minus TA, which is equal to T naught B minus TB, right? So now what I can write is T naught B minus T naught A, T naught B minus T naught A is equal to TB minus TA. So I can write in this way from the given information. Okay, the addition of heat is nothing but T naught B minus T naught A is in terms of TB minus TA, the rise in static temperature. For a reason, we know that TB is greater than TA, right? TB is greater than TA, so that means T naught B is also greater than T naught A. That's understandable. Okay, so now look at the options carefully. Which of the following statement is true about flow field? So they are given option A, flow is subsonic and MA is less than MB. The flow is supersonic, MA is greater than MB. Flow is subsonic and MA is greater than, MA is less than MB in option A. In this case, MA is greater than MB. Flow is supersonic with MA is less than MB. So which of this option is correct? To address this one, somehow we have to bring into the eye of Mach number. So to state it carefully. So by looking at the graph, you can make an educated guess, but it's not a good way to do that. So for this, what we can do is, I have a definition like T naught B by T naught A is equal to T naught B by TB times TB by TA times TA by T naught A. This is one way to do that. Or the straightforward way is, yes, the straightforward way to do this is use the idea of this stagnation property change, right? So what we can write is T naught B can be written in terms of TB times 1 plus gamma minus 1 by 2 times MB square. Similarly, T naught A can be written in terms of TA times 1 plus gamma minus 1 by 2 times A square. So now let us call this as equation 1 and equation 2. So subtract this equation. So what I get is T naught B minus T naught A left hand side, which is equal to TB times 1 plus gamma minus 1 by 2 times MB square minus TA times 1 plus gamma minus 1 by 2 times MA square. So now I can take this TB inside and TA inside. So this becomes TB minus TA plus gamma minus 1 by 2 common times TB MB square minus TA MA square, right? So left hand side I have T naught B minus T naught A, and from the given statement that stated delta TA equal to delta TB, right? From here we obtain the relation that T naught B minus T naught A is nothing but TB minus TA. So this and this are same. So we can cancel this out. So what I get is gamma minus 1 by 2 times TB MB square minus TA MA square equal to 0. So this gives me a relation between T and M. So that is nothing but TB MB square is equal to TA MA square. So now I can write in terms of MB by MA, which is equal to square root of TA by TB. So now it's a straightforward, right? So I know TA is less than TB. So because TB is greater than TA, so from the curve, we can recognize that. So that means this is going to be square root of 1 divided by some number which is greater than 1. So that gives me MB by MA is less than 1. So that means MB is less than MA. Right? MB is less than MA. So now look at the option very carefully. Wherever MB is greater than MA, you can strike out, right? MB greater than MA, you can strike out that option. MB greater than MA, because we saw that MA is greater than MB. We just solved it. Right. If MA is going to be greater than MB, and we also know that T naught B is greater than T naught A, that means we are adding the heat. We are adding the heat, and my lower point MA is greater than MB. So when it can happen? So if I add the heat as well as Mach number is decreasing. So that means flow is decelerating by adding the heat. So that can happen only in the supersonic case, right? So that is why the option, so in the subsonic case now vanishes. The only option which is correct is flow is supersonic with MA greater than MB, right? So this is interesting problem, very, very good problem. It's asked in 2017. Okay, so let us stop our discussion over here. If you have any queries, you can contact us at IT in Gate Classes. And thank you for your attention.